Let us now derive the change in entropy for an ideal gas in terms of the variables pressure, volume and temperature. For that, we will begin with the second law of thermodynamics, the first law of thermodynamics, which is dq is equal to du plus dw. This is the change in heat of the system, change in internal energy of the system and work done. We know that by definition du is just cv dt and dw for the mechanical work is p dv. So let us just substitute here. Further, we also know by definition that ds is dq divided by t. So let us use this expression for du and use this expression for dw into dq, and let us write that dq here so that we get dv dt plus p dv divided by t. Thus we have ds equal to cv by t dt plus p by t dv. Let us just call this as some equation A. Now this is a general equation, and now we will try to derive the change in entropy in terms of any two of these three variables. So there we will have three different formulae involving P, V and T. So suppose there is a system which goes from state 1 to state 2. Accordingly, the entropy changes from, say, some value S1 to S2, and this change in entropy delta S, which is S2 minus S1, could be found out by integrating the equation A. Integrating the equation A from 1 to 2, that is from state 1 to state 2. So integrating equation A, we get integral from S1 to S2 ds is equal to integral cv by t dt plus p by t dv. So this just gives us S2 minus S1, which we have called as delta S, which is the change in entropy. So delta S is now integral cv by t dt plus p by t dv. This is the equation which we are going to use for further derivations. Now let us just do the first part of the three expressions. We know that for an ideal gas, 1 mole of an ideal gas, PV is equal to R times T. So this means P is RT by V. Now if we substitute equation 1 in B, we get delta S equal to integral CV by T dt plus RT by V dV. Note that R is a constant, also CV is a constant. So just a minute, there is a T here. Okay, so this is what we have now, CV by T dt plus R by V dV. Since CV and R are constants, they are taken outside the integral, and 1 by T dt is log T. So this is from state 1 to 2. So similarly, the limits are T1 and T2 plus R times log V. Again, 1 by V dV is integral is log V from some volume V1 to V2. Now log T2 minus log T1 is written as log of T2 by T1 plus R times log V2 minus log V1 is written as log of V2 by V1. So this is change in entropy for an ideal gas in terms of the variables temperature and volume. Now similarly, we can derive this delta S in terms of pressure and volume, and then temperature and pressure as well. So just like this formula, we have to derive two more formulae for delta S. We are just going to change the variable accordingly within the integral sign. Let us do the second part of the derivation now. We will start with the ideal gas equation again. PV is equal to RT. Now if we differentiate this, we get first into derivative of second plus second into derivative of first, P dV plus V dP equal to R is a constant, so it is R into dt. That's it. So this is an expression. Let us call it as equation 2. Now we have to use this equation 2 in the previous equation, that is this equation B. Note that we have here PdV, and instead of PdV, now we can write from 2 PdV equal to R dt minus V dP. This is same as equation 2. We are just changing the terms from left hand side to right hand side. So instead of this PdV appearing here, we have to write this entire expression. So we have delta S equal to integral Cv by T dt plus R dt minus V dP divided by T, right? So this PdV is replaced by this term. So this is equal to integral Cv by T dt plus R by T dt minus V by T dP. Now we know another relation called as Mayer's relation. Mayer's relation, which gives us an expression P between Cv, Cp and R. And we know that Cp minus Cv is equal to R. So what we are going to do, that instead of R, we are going to write Cp minus Cv. This is equal to integral Cv by T dt plus Cp minus Cv by T dt minus V by T dP, right? So this is equal to, now this Cv by T dt gets cancelled with this minus Cv by T dt, and we are left with Cp by T dt. So Cp by T dt is left out, minus now this V by T dP can also be replaced again, since from ideal gas equation PV is equal to RT, we have V by T is equal to R by P, right? V by T is equal to R by P. So instead of V by T, we will write here R by P dP, which is equal to integral Cp by T dt minus R by P dP. Now the variable has been changed to pressure and temperature. Now this is again the same type of integral. Cp comes outside being a constant. Then we have log of T2 by T1. Since 1 by T dt integrated gives us log T, and accordingly the limits log T2 minus log T1 gives us log T2 by T1 minus this R comes outside, and we get log P2 by P1. So this is the same expression modified for variables temperature and pressure. Earlier we were discussing about the variables temperature and volume. Now we have with us temperature and pressure, right? So now the last part remains, that we have to do it for the combination of variables pressure and volume. For that, again, we will begin with the ideal gas equation. PV is equal to RT, and we will write it as T equals to PV by R. So call it as equation, say equation 3. Further, if we differentiate this, we get R being a constant, it is just remains as it is. dt is equal to P dV plus V dP. This is what we have for dt. Note that we are doing this because now we are seeking for delta S in terms of pressure and volume. So we are going to eliminate the variable T. So instead of dt, we have to replace something. And this is that something which we are going to use. Now, let us look at this equation again. Equation B, delta S is integral Cv by T. Let us just carry forward this equation. Delta S is equal to integral Cv by T dt plus P by T dV. Right. Now, wherever T appears, we have to replace it by equation 3 and equation 4. So this gives us integral Cv by PV by R. Instead of dt, write it as 1 by R P dV plus V dP. This is the first term, plus P divided by, instead of T, we write it as PV by R into dV. Now this can be simplified further, and we will get integral Cv dP by P plus integral Cp dV by V. That's it. So this is a very easy expression. We can see that P disappears, R comes outside, and we get 1 by V dV. Similarly, here many things are going to disappear. This R, then this P, then this V, and this can be further simplified to get this particular expression. Now we can integrate it easily to write Cv log of P2 by P1 plus Cp log of V2 by V1. So this is the change in entropy of an ideal gas expressed in terms of variable pressure and volume. So any of the combination of two variables of the three variables, namely pressure, volume and temperature, can be used to determine the change in entropy of an ideal gas when its state changes from state 1 to state 2 in general, provided that we know the values of Cp and Cv, that is the specific heat at constant pressure and specific heat at constant volume for the given ideal gas. Thank you.